Great. Well, it's time for a little talk about biostatistics. I was really pleased this year to get the chance to talk with you about difference tests because I think difference tests are probably the number one application of biostatistical concepts, and there are a lot of ways to follow it up. So I would like to try to give you some background to avoid making mistakes as you use t-tests in biomedical research. So today we'll be talking principally about p-values, the way we derive them via t-test and u-test. But I'm going to start with a little bit of the history that led to our use of the t-distribution in particular, and also a little bit about a successor to it, the Wilcoxon approach. We will talk about several examples of doing difference testing within R. The homework assignment that you have associated with this already appears on Moodle, I think. And the homework will be evaluated in a practical immediately following the lecture on Thursday. So I believe today, Guillen will be talking about the homework that stretches forward from the prior thing. I'm not able to do a practical session with you on Friday because I've got a meeting scheduled at that time. So we're just going to do one practical from the two lectures I'm responsible for. Hope that helps. Okay, so we're going to start with a statistical history of beer and bullets. From there, talk about test statistics and p-values, and to go into some examples of difference testing in R. So today is really all about cohort versus cohort studies. You've got a bunch of examples of A, you've got a bunch of examples of B, and you want to know what changed. So we're going to start with William S. Gossett. Maybe people haven't been that forthcoming about it, but it's customary for people to think of the various luminaries in the field of biostatistics as if they are solely represented by this snapshot of that person looking very distinguished at a particular meeting, someone who sits around thinking very big thoughts and amazing papers come from them. But in fact, the history of the people who put together much of the background in biostatistics is colored with interesting history. And one of the first things to know about the community in British academia that put together a lot of the framework for biostatistics is that they hated each other with a brutal passion. And so it's kind of interesting, I think, to get to know them as people. And along the way, we're going to be looking at four different people: William Gossett, Frank Wilcoxon, Mr. Tukey, and R.A. Fisher, of course, our great vaunted luminary in the sky of biostatistics. So let's start then with William S. Gossett. As you see, in 1876 he was born. He joined the Guinness Brewery. Does anyone like a Guinness? No one likes Guinness? Yeah, you do. That's good. You know, I thought I hated beer in general, just point blank. And then I realized that stout from Guinness is actually pretty good. So he was working at a very early year in Guinness Brewery after earning his chemistry degree at Oxford. He had a leave of absence in 1906, back when universities did that sort of thing, and he worked with Carl Pearson at UCL, University College London. And while he was there, he did work that later led to his studies of the t-distribution. The t-distribution is the thing we actually compute in a student's t-test. From the t-distribution, we learn the p-value. So by knowing the distribution of the t-statistic, we're able to compute or estimate p-values from a given t-statistic. Okay, so that work happened all the way back in 1906. Now, why did he publish under the name student? It happened because he wanted to publish in his own name, Mr. Guinness, but he was not allowed to do so by his company because they didn't want other breweries to know that they'd hired somebody to think about statistics for them. So he was prevented from attaching the name Guinness to his test, and instead it goes under the name student. Therefore, when you write in your master's proposal that you are going to use student's t-test, always capitalize student, because it's a person. All right, a lot of people lose that point. And one of the things I would say about William Gossett that might be some of the highest praise I heap on any biostatistician is this final point. His mild personality helped bond together the contentious British statistical community. People who were really invested in hating each other found that if they hung out with Gossett, they could explain their ideas, and Gossett would get those ideas transmitted more broadly, that he was somebody that other people didn't hate, and therefore he could be a middleman in a lot of respects. So we can praise that about him. Now, I also like Frank Wilcoxon. I'm going to talk about several names for the U-test, and sometimes I might even slip and call it a W-test. The T statistic is all about Gossett, and also about a subsequent change called Welch. So if I talk about Gossett, student, or Welch, I'm talking about T-tests. If I'm talking about Mann, Whitney, or Wilcoxon, I'm talking about a signed rank test instead. This is a sum rank test. That's the U-test, or sometimes called the W-test. So these are counterparts to each other. We have a parametric test, the T-test, and we have a non-parametric test, the U or W-test. We'll try to explain those differences as we move ahead. So Frank Wilcoxon has a really interesting kind of history. He was an American, but he was born in Ireland, which would probably lead to a great deal of confusion. He completed his PhD in 1924. How old would that make him at the time he got his PhD? We can do the math. In my mind, that's 24 plus 18, which comes to, what's that? 42. So he was 2 years younger than I am now when he finished his PhD. And yet Frank Wilcoxon had a huge impact on statistics. So we start with his role in World War II. A lot of people might not think of wars as a particularly good time for intellectual advancement. But there are a lot of times in war that governments want immediate answers on whether going this route or that route is best, because they are so constrained in the resources they've got and the immense challenges that they are undertaking. So he worked in arms manufacture. I would just point out that my father spent most of his career at the Army ammunition plant in Kansas City. Seeing that Frank Wilcoxon managed to keep people like my father from dying in World War II gives some sort of a warm space for me. So his second paper, the second paper he ever published, was about the use of ranks rather than magnitudes in difference testing. So when we think about something like Ttest, we think about the original values that we provide being used to ask, is there a difference between this cohort and that cohort? In Frank Wilcoxon's tests, though, we ask how the ranks of these items differentiate them between cohorts. So his rank sum and signed rank tests were created all the way back in his second statistics paper. And as you can see, he was a fond rider of motorcycles. I just couldn't resist that photograph of him in the upper corner. All right. So behind the scenes, in a difference test, we're going to compute a test statistic. I've already alluded to this, but it's a good thing for you to know. A T-test combines the information from the values we see in order to produce a T statistic. That T statistic can then be used, can be translated more or less, to a p-value. So the student T-test isn't just producing a p-value straight out, it's producing a T statistic. The T statistic is used as a lookup then to get to a p-value. And the same is true of the Mann, Whitney, or Wilcoxon test. Here I've drawn it with the typical U used as the test metric. So let's walk through these equations here. When we look at the top of the fraction here for the student T-test, that's the numerator, am I correct? Bottom is denominator. Does everyone remember that stuff? Okay, I haven't miscalled it, that's good. It's been a while since I thought about numerators, but when we look at the numerator of the T statistic, we're looking at x sub 1 bar minus x sub 2 bar. All right, that might be a little confusing for folks, so let's just define it. X sub anything bar is the mean of these sample values. So if you have 5 numbers that correspond to cohort A for this particular analyte, you can compute the mean value of those 5 values, and that's what we substitute in for x sub 1 bar. We can do the same for our other cohort. We have a bunch of values in cohort B that we saw for this particular analyte. We can find the mean value of those 5 values as well. So in effect, we're looking at the mean value from cohort A minus the mean value from cohort B. That's the numerator. So if you want a really big T statistic, correspondingly a really low p-value, you want to see the mean difference be large. If you have a very small mean difference, your ability to find to detect it is a lot weaker. So the bigger the mean difference, the better. Now on the bottom, we have the pooled standard deviation multiplied by the square root of 2 divided by n. All right. The important, if you're doing a 5 by 5 study, then you're going to have this that the n value is fixed. So in effect, what rules your ability to determine a difference here is to have a nice small pooled standard deviation, very small pooled standard deviation. Now, I think at this point you've probably had a little more exposure to the normal distribution than the last time we talked. Do you feel comfortable about the normal distribution? Not everyone feels comfortable about the normal distribution. All right, that's fine. Let's talk about it. In a normal distribution, we have a peak at the center, a midpoint in this distribution that is its highest, most probable location. So this is the mean value. So every time you think of a normal, you should always think it's centered on some mean value. If you then draw a vertical line across this distribution, one standard deviation away, one standard deviation down, one standard deviation up, you have some fraction of that normal distribution found within those limits. Yes?
What is the standard deviation?
What is the standard deviation? It is the square root of variance. But I realize that's a very glib answer, but you've not mentioned standard deviation at all in this class?
Yeah, we have.
Oh, okay. Yeah, the standard deviation is computed from the variance information. So empirically, you must look at the data to see how they're spread in order to compute what the variance is and what the standard deviation is. Okay, so if you're starting at the midpoint, at the mean of this distribution, and you go one standard deviation down and one standard deviation up, what fraction of all of that distribution should fit inside those two bounds? What's that?
Fraction 1 of it.
A fraction, yeah, out of 100% of all of those values, what fraction fall within those bounds?
95.
No. 68%, that's right. Yeah, so 68% of the value, about 2/3 of this distribution is going to be found within one standard deviation. If you move out to 2 standard deviations away, you can now explain about 95% of the data. If you scoot even further to 3 standard deviations, you can usually account for 99% of the data. So if you have a...
Can you repeat?
Oh, sure. Okay. So how many values fall exactly on the mean? Possibly 0, right?
Yes.
Maybe 1 or 2. If you have exact ties right at the mean, that could happen. So we start with nothing explained. We scoot out 1 standard deviation. Now we've explained 68% of all this distribution. We move out a second standard deviation in both directions, and now we explain about 95% of the data. And if you step out 3 standard deviations, you've usually accounted for 99% of the distribution. We can run that test as well. Within R, you can sample abnormal distributions quite easily. So, all right, so having computed standard deviation from the samples for both of these cohorts, having computed means for either of them, and knowing how many samples we have in, in our 5-on-5 comparison or whatever, we can compute a t-statistic. So that's how students' t-test works. It creates this t-statistic. From there, we can look up a p-value. The u-statistic is a bit different, and it might be a little confusing. So I'm going to ask you a basic question. Let us say that we have 3 items in a list. We have one that has the top value, one that has the median value, and one that has the minimum value. Okay, so elements ranked 1, ranked 2, and ranked 3. What is the sum of ranks for our set of 3 items? The answer is easy on this one. What's the rank of the top one?
1.
Number 1. What's the rank of the second one? And the rank of the third one? Okay, so the sum of ranks for a list of 3 items is 6. 1 plus 2 plus 3. All right, so in Mann Whitney, in the Ttest, that will also be kind of fudging and calling the Wilcoxon test. We're asking about the relationship of the sums of ranks for 2 cohorts. So imagine in a simple 3-on-3 Ttest, I have items for cohort A that are all above the items for cohort B in rank order. So for cohort A, I have ranks 1, 2, and 3. For cohort B, I have ranks 4, 5, and 6. So I can compare the sum of these ranks as a way to evaluate how well separated they are. If they're commingled with each other, where cohort A has one that's at the top, cohort B has one that's second best, cohort A has the third, cohort B has the fourth, cohort A has the third, fourth value, fifth value, etc. Then they're commingled, right? They're interlaced with each other. So by looking at the sum of ranks for the items from cohort A and cohort B, I can also ask, are they different or not? Okay, so the math for Mann-Whitney produces its U metric by the math that I show up on screen, and it relates to the fact that we can compute what ideal rank sums should be for separation. All right. Both of these are built around the idea of a null hypothesis. The null hypothesis is written a little bit differently for students' Ttest than it would be for Mann-Whitney or the Wilcoxon test. So under the Ttest, we say that the null hypothesis is that there is no difference between the means of these two populations. So when we compute a p-value, it's evaluating that null hypothesis. So if the null hypothesis is a very good explanation for the way the data spread in space, then we're not going to overturn it, and we're going to give a very high probability of correctness for the null hypothesis. If, on the other hand, these data are spread very far from each other with a very low variance within each population, we're much more likely to say there's a very low probability that there's no difference between the population means. So that's the null hypothesis driving t-testing. There's also a null hypothesis for something like Mann-Whitney or the Wilcoxon test, which is to say that if you chose a random item from the A cohort and a random item for the B cohort, there's no greater chance that the A will be greater than the B or vice versa. Right, so that's kind of a confusing way to put it, perhaps, but the null hypotheses are slightly different. But in each case, for the biomedical researcher, it amounts to roughly the same thing. If you have a high probability attributed to this null hypothesis, in other words, a high p-value, then you say, well, there's no real difference between A and B, which is kind of a sloppy way to speak about it, but that's what we say typically. So if you were seeking a difference between these sets of numbers, you would expect a low p-value. Okay. Right. So I wanted to point out then that Gossett, that the big advantage he had in 1908 was that he found a way to compute the probability that you would have a more extreme t-statistic by random chance, thus giving him the ability to not just generate these t-statistics for a difference, but also to say what is the probability that you would have a value this large by random chance. So what does this t-distribution look like? Here we go. So the probability associated with the t-distribution shrinks as you get out to the ends, basically. If you have a very high or a very low t-statistic, that's going to give you a very low p-value. So it's an inverse relationship. A high t-statistic drives the p-value down. Oh, and the other thing I should mention here is that it depends upon degrees of freedom. This is another concept that shows up in a lot of statistical concepts, and it's here again. So if you are using 50 values in each cohort, 50 samples in each cohort, you're going to use a different t-distribution for looking up your p-value than you would if you had only a 5-on-5 comparison or a 3-on-3 comparison. So you can see that those distributions change a little bit. Now, one of the cool things that he noticed here is that the t-distribution looks quite a lot like the normal distribution. So if you look at these round dots, that's what the normal distribution would look like for these values. And you can see that as the number of degrees of freedom shrinks, as you have fewer and fewer samples, you get further and further away from the normal distribution for doing this lookup. Okay, so the thing I would really like you to keep in mind here is that if you're running a t-test, you are computing a t-statistic based on the formula we just looked at, and that t-statistic is then used for looking up a p-value associated with it. Okay, Now, if you run a t-test in R, and you simply run it by the defaults, you are not running t-test as Gossett originally envisaged it. If you're running a t-test in R without changing this parameter, it will instead run a Welch test. Why does it do that? It does that because if you are comparing numbers that have different distributions for these two cohorts, you're going to run into a big problem in the t-statistic that you compute from it. So in this case, you can see that only the denominator has changed. We're just changing how the standard deviations are constructed. You compute a standard deviation for cohort A values, and you can construct a standard deviation for the cohort B values. And those get used individually based on the number of items in each of those cohorts. So I've drawn an example here for why you might care about that. So here we have a black distribution and we have a red distribution. Both of these represent exactly the same number of values. I've got 1,000 samples in the normal distribution that's black and 1,000 in red. But as you can see, the standard deviations are different for these two populations. For the red distribution, it's quite narrow. For the black distribution, it's quite wide. If you were to run a t-test on values distributed like this without the Welch correction, the software would assume that the distributions were equal in spread. And clearly, in this case, they're not. Now, if you have only a 3-on-3 comparison, your ability to detect that your standard deviation is much wider on one side than on the other sort of goes out the window. You don't really have a lot of power to detect that in that case. So I've given the example here of 1,000 points to make it very obvious that the distributions are different. But in the back of your mind, you should be thinking, if I run a 3-on-3 experiment, do I really know whether the deviation is wider on one side than on the other? You can imagine a scenario where that would be obvious, where this point is way down here and this one's way up here, and this one's the one in the middle. That's very wide, whereas the other one might be very tightly grouped. But sometimes that apparent difference in variation happens just by random chance. And in a case like that, it may not be apparent that you need to use the Welch correction. So frequently, people will just default to use the Welch test rather than the t-test, per se. It's still generating a t-statistic, but the way it computes the standard deviation is different. Okay, so does everyone get why the spread of those values is problematic? In this case, we want the original student t-test, as published by Gossett, expects that the variance of the data is just the same on both sides, and it may not be the case. So if you run t-test in R, without modifying this behavior, it's going to use the Welch correction instead. All right. Now, your homework is going to emphasize this rather heavily, so I want to make sure that everyone gets this point. One of the things that we must always keep in mind whenever we're running a difference test, whether it's a t-statistic or a u-statistic, is whether our data are paired and whether our data are one-sided or two-sided. So let's say that we were trying to evaluate whether the honor students in 2018 knew more about statistics at the start or at the end of the biostatistics unit. I got one joke there, one laugh there, so I'm happy. That's good. So imagine that we do a pre-test, and then we ask you exactly the same questions 2 weeks later after you've made it through this amazing experience that is our biostatistics module. We probably have a hypothesis associated with that. And we have a pairing structure associated with that. If I'm looking at Luto's experience of biostatistics, I'm going to ask, what is his score at the start and his score at the end? It doesn't make sense for me to compare Minka's post-score with Luto's pre-score, for example. So this is clearly a case where we have a paired experiment. A particular value in this cohort relates to a particular value in this other cohort. Anytime that's true, you have a paired experiment. And if you fail to use paired as an option on the t-statistic, you're not going to get the correct p-values out. The software must know that the second value in this cohort relates specifically to the second value in this cohort. That is a paired statistic. Now the other part of this is that we presume, as professors, that by sitting through 12 days of biostatistical training, that your scores are going to get better on this test. If they get worse, we feel very bad, right? We haven't done our jobs. So our hypothesis here is not that the scores will be different between pre and post. Neither, these two outcomes are not equivalently good to us. We expect that we have lower scores for students at the start and higher scores at the end. So in this case, we don't just have a pairing that takes place in our t-test, we also have a one-sided hypothesis. We expect that scores are greater after this module than they would be before. All good with that? This shows up in all kinds of different tests. So if you expect that one of your cohorts is going to have a very powerful immune response and you're measuring cytokines, then you probably want to look at markers of immunity with a one-sided test, the assumption that they should be going up, and we don't actually care about the things that are going down. So that is, those are the concept of pairing and of one-sided versus two-sided tests. All right. This is a concept that I hit several times, I think, in the bioinformatics module, but I want to re-emphasize it here. As we saw in the numerator of our statistic, we saw that the value would go up if we had a difference between mean values. Everyone remember that? X sub 1 bar minus X sub 2 bar. We want the difference between means to be very, very great. But there's another part to that. We also want the variation within cohorts to be very tight. So in this case, I have two different distributions. The mean value for blue is set to -1 in each of these. So this should fall right over -1. This should fall right over -1. And the mean value for red is at +1. So this is the mean for red. This is the mean for red. So we have the same mean difference in both of these cases. But at the left, I'm showing you a plot where our standard deviation is set to 1. At the right, I'm showing our standard deviation is set to 2. As a result, those distributions are wider. So this is something that should always be in your mind. It is not enough to have a separation in the mean values. You must also have the numbers be relatively tightly grouped around that mean. So having a low standard deviation in your data makes it easier to detect a relatively small mean difference. Now, if we were to do anything around power, I don't think we have a lecture on estimating power. It's actually a very difficult concept. But one of the concepts that we talk about very frequently in power is effect size. Essentially, how big a change do you hope to be able to detect? So as you might expect, if you're doing a power analysis and you have very low variance associated with your measurements, you're in a much better position to detect small fold changes or mean differences, either way. So always bear in mind that a difference in mean value is not enough. We also need to have a small enough variance that those mean differences are detectable. All right, how does it look when we run these t-test applications within R? I've done a whole lot to simulate data in these, so I'll try to walk through these. We have a big stick in here, don't we? Oh, we do. Brilliant. I always prefer the big stick to a laser pointer. Okay. So here we go. We have 5 values that we're going to stuff into the A variable. And they're drawn from what kind of distribution? Normal. Right. So in this case, we're configuring what that normal distribution looks like. We're setting the mean to -1, and we're setting the standard deviation to 1. So when you think about it, you should say in your mind when you read that, okay, 68% of the values from this distribution should fall between two values. What are they? The standard deviation is 1. So 68% of my values should fall between what two bounds?
-2 and 0.
Brilliant, yes, exactly. So the mean is at -1, standard deviation is 1, therefore the left bound of that 68% set is at -2, and we also have to compute it for the upside. So the other side of that is at -1 plus 1, which is 0. So 68% of the data from this sampling should fall between -2 and 0. Thank you. Yeah, that's exactly right. We're doing the same for B, but here we've changed where that mean value sits. So 68% of these values should fall between 0 and 2. Okay, so there's going to be a little bit of inner feathering of these two distributions. If you sampled 1,000 values, you'd expect a whole bunch of them to fall in this fringe zone where they overlap. Overlap is a little challenging for us to deal with in Ttest because that reflects a non-complete separation of our two distributions. Okay, now I've been very lazy because I just wanted to plot what values came out of this sampling. So I used a simple bar plot function, binding these together and running them beside. So you can see that our 5A values were between -1 and -2, maybe -2.6 or so, about -0.5, -2.3-ish, and maybe -1.8, something like that. And you can also see that the B values are mostly positive, but some of them are very slightly negative. Okay, this is just the luck of the draw. If you run this code 1,000 times, you get 1,000 different sets of values. Now we want to run a t-test on them. And the function for doing this in R is straightforward. T-test, A comma B. That's the simplest kind of call. But one of the things that I've tried to warn you about here is that when you run t-test like this, it doesn't run student's t-test per se. It runs the Welch corrected t-test. And the Welch corrected t-test assumes that the distribution, that the variance of these two distributions are unequal. All right? So this t-test might seem like you should just run it as is, the simplest call possible. But in this case, in its output, we recognize that it has computed a Welch two-sample test, not the originally Gossett published student's t-test. So we get a t-statistic. There it is, -4.0638. Is that good or bad? Well, it's going to be interpreted through the number of degrees of freedom that are involved, whether you've used pairing, whether you've used one-sided or two-sided tests. So it's going to give us information about that. The degrees of freedom here are set to 7.5563. I'm not sure how it gets to that number. It's got a p-value that is looked up from this t-statistic, and it's reported right here. Now, frequently, that's the only number people care about. When they look at their t-test output, they just ignore anything that has anything to do, anything about the p-value, just grab the p-value itself. That is a mistake, however, because you want to make sure that the t-test you ran is the one you intended. So, we get valuable information back. So in this case, the alternative hypothesis is essentially 1 minus the null hypothesis. The hypothesis we're testing is that the means are the same, but in this case it's rejecting that null hypothesis. So this Boolean reflects whether we reject that null hypothesis or not, and then it translates that. Difference in means is not equal to 0. Okay, so it's translating that to words for us, and even better, it's giving us confidence intervals so that we can say how stably do we know this. If you have 10,000 values rather than 3 on 3, your ability to come down on one side or the other of this decision about whether the null hypothesis is true is a lot more stable when you have more n. All right. So this is its estimate of the mean. This is its estimate of the other mean. So how do these compare to the true values? What is the mean of x in this case, of the first distribution? It's reported right up here. We sampled it, right up here rather. We sampled 5 values from a distribution with a mean of -1. We sampled 5 values from a distribution with a mean of +1. So the mean of x really is -1. The mean of y really is +1. But you see, because this is a random sample, the mean value for the sample is different than the mean value for the distribution it came from the population. And here, it's reporting what those values really are. So it's a good reminder to you when you're making simulations of different t-tests to check to see how much walk-around there is. Just by sampling a different set of numbers from this distribution, you may find that the mean values drift a fair bit from what the population mean really was. Okay, on we go. Now, when we do the U-test or the Wilcoxon test, it's going to be a little different. Now, I've once again sampled 5 values from a mean of -1, 5 samples from a mean of +1. And you can see that, in this case, the B values were all positive except for this last one. And oddly, in the case of A, one value was also on the other side of 0. So there's some intersection then between these two distributions. In this case, we can compute the W value, and it's 2. It's 2, not 2.1638, whatever, it's just 2. From that, we get this p-value, 0.03. So in this case, the true location shift is not equal to 0. It is interpreting that to say that if the null hypothesis for this U-test doesn't hold water, that the data are more different than we would expect by random chance alone. Okay, so in this case, we're running just the Wilcox test. I've talked a bit about the Mann-Whitney U statistic. This is the Wilcoxon variant of the same thing. It produces the W statistic. Practically speaking, there are differences. I'm honestly not that clear on them. So a lot of times you'll hear people talking about these as rank sum tests, and sometimes you'll see them called the Mann-Whitney-Wilcoxon test or the Wilcoxon-Mann-Whitney test, depending on who's doing the writing. But in each case, these are non-parametric tests. So one of the key things to note about this is that the Ttest is really great when your data are normally distributed, when they have a nice clear mean, when they're symmetric around that mean, and so on. If your data don't meet that qualification, the U-test or W-test is frequently a much more reliable way to evaluate them. So what does that look like? That's one of the reasons we call it a non-parametric test. It is not reliant on a particular distribution of the data. So let's look at some scenarios where that comes in handy. So in this case, our A is once again sampled from values with a mean of -1. But you see I'm only grabbing 4 values from it. And then I'm sticking onto the backside of this a real outlier. So 4 of the values in A are random. The 5th is the value -10. Over here, I'm still drawing sample B the same way. I'm sampling 5 numbers from a mean of +1, standard deviation 1. So the numbers are coming from the same kind of distributions as I showed in the last 2 slides, but one of them is a ringer. I've hard-coded in a big outlier, a very largely negative value, to go in alongside the rest of this distribution. Let's look at how that distorts things. When I run Ttest with Welch's correction, I get a p-value of 0.17. No one would say that's actually differential at this point. This is the Ttest is well over 0.5. No one is really going to be mistaking that. But when I look at the U-test value, I get a very strongly significant result. Why is that? Well, remember that the data need to be clustered pretty tightly together for us to get the ability to detect mean differences. So if your data are very widespread in one or the other cohort, you're going to have a problem. Having thrown in this big outlier, this value of -10 right here, I've caused Ttest to lose certainty that these means really are different because one of the cohorts is really wide, and it no longer feels comfortable making its declaration about whether these distributions are different or not. But U-test barely blinked. So if we can talk about this for just a moment, I want you to think of the U-test as a little Scrabble rack. Does everyone know how to play Scrabble at least once in your life? There's a little wooden rack that you put your little tiles on so you can see them and your opponents can't. So imagine I have a Scrabble rack, and I have, in this case, 5 white balls and 5 black balls. So the 5 black balls represent the A values, and the white balls here represent the B values. If I have these just plunked down into the tray and sort of roll that tray back and forth, it might have been that the values in the white marbles were quite close together to begin with. The ordering isn't going to change as I rotate this Scrabble tray around, but the magnitudes of them will. So if I have 5 white marbles and 5 black marbles, what's the most separated they can be in my Scrabble tray? All of the black values above all of the white values, or all of the white values above all of the black values? So if I'm just looking at how they line up on this trough, if all of the whites stay together and all of the black marbles stay together, we have a perfect separation of all of the whites from all of the blacks. Now, if I swap that middle pair, I'm going to just use my fingertips for the marbles for just a moment. I should have just brought in a Scrabble trough. That would have been more straightforward. If I have 5 white and 5 black marbles, this is a perfect separation. This is the first crossover for them. Now I have 1 black marble below one of the 5 white marbles. So what I want you to think of is that this is the lowest p-value I can get for 5 marbles versus 5 marbles. That's the lowest I'm going to get out of Wilcoxon. If I have 1 crossover in that, where just the middle 2 marbles are swapped, I'm still going to get a pretty low p-value from it. But think about what happens if I've got my fingers totally interlaced. Now I'm looking at a pattern in this trough of white marble, black marble, white marble, black marble, white marble, black marble, etc. This is the most indifferent kind of p-value you can possibly get from a Wilcoxon. And you can keep moving until the white and black marbles are completely crossed from each other. In a case like this, all of the whites are separate from all of the blacks, and once again, we have the lowest p-value you can get from a Wilcoxon test or a Mann-Whitney. So there's this kind of stair-stepping that we see in the p-values that come out of Wilcoxon. And the more marbles you have, the more replicates you have, the more possible combinations there are in how these can be overlapped from each other. You might have 2 white marbles that are each lower than the highest of the black marbles, for example. That's one of many possible interlacings of black and white marbles here. So Ttest freaks out. Ttest looks at this and says, everybody out of the pool, I see that in the A distribution, I have a very, very wide distribution. That's going to really challenge the p-value. But Ttest doesn't care, because Ttest does not care about the magnitudes of the original data. It only cares about the ranks of them. So to return to our marble analogy, the rightmost marble we have is white. The next is white. The next one is white. The next one is white. The next one is probably white. And then we have black, 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 black. So to Ttest, this is perfect. All of the white values, so all of the A values are lower than all of the B values. That's an ideal separation for Ttest. But for Ttest, the fact that the magnitude of this individual element is so far out of line with the others is a huge problem. Okay, now let's look at the paired one-sided values. Now in this case, I am not using the normal distribution for A. Does everyone recognize what RUNIF points to? We've been looking at R norm. This is R unif. Okay. This is the uniform distribution. So a uniform distribution is really good when you want to get a value that's picked from any location between these two. I think Guillen was showing you some of my dice from tabletop board gaming. So if I have a 20-sided die and I roll it, there's no greater chance that I roll a 10, which is close to the mean, than I roll 17 on the single 20-sided die. It's a uniform probability generator. It has a 5% chance of landing on any particular face of the thing. In this case, we're not using a die, we're using a distribution. So these values are going to be continuously distributed. You know, it's not 0.05, then 0.1, then 0.15. Instead, it's every possible value between 0 and 1. So those 5 values are going to get drawn into A, and I'm multiplying them by 5. So the maximum value that could be drawn in computing A is 5, because by default RUNIF ranges from 0 to 1. And the lowest possible value that could be sampled in A is 0. It's going to give us 5 random numbers. So here I have drawn those values into A, they're drawn in black on the box plot, or the bar plot beneath. Now B is going to be set relative to A. You see this? So I'm going to add a number from the normal distribution to A. What is the smallest value that a value in B can be? That's kind of a hard question, isn't it? Okay, let's start with the fact that the values of B are built upon the values of A. So what's the smallest value that a value in A can be? The smallest value Runov can kick out is a 0. We're multiplying that by 5. Therefore, the smallest value that an A could be would be 0. And then we're adding the absolute value of a normally distributed number, mean of 0, standard deviation of 1. So the smallest this part can be is 0. Therefore, if you had an A value that was 0, the smallest number that you could get out of it in B is also 0. Okay. I just wanted you to think about how I'm using these numbers. So in each case, I have a paired relationship in B, because each value in B is going to be some amount higher than the corresponding value in A. All right, so now when we run a t-test on A versus B, we specify that they are paired. We're specifying that they're paired because the third value in B can only really be judged by knowing what the third value in A is. Everyone see that? This is kind of like the student pre-test and post-test thing. So here we're adding on some effect. So let's say that A is a pre-test score and B is a post-test score. How much have we added to the student's score by going through a 12-day biostatistics module? All right, so if you look at the A and B values, we see that in this case, the value of the first in A rose from 3.2-ish to about 5. In the second case, we had the lowest value of the A's, somewhere like 2.4, and it rose to about 2.6. Over here, we had a huge jump. We had a value of almost 5, which is very close to the maximum for A, and we have a rather big jump to its corresponding B value. So now we want to ask, did the process of this experiment, the thing that changed from the value at A to the value at B for each individual, did it have an impact? And we're doing so using an alternative hypothesis of less. We're saying that that we anticipate these numbers are going to increase. So we're not really going to be sensitive to the fact that some students actually get worse when they go through this. Our model says if you train students, their grades get better on this instrument. Okay, so as written, I get a p-value of 0.03, which says that yes, there is an increase from the A value to B for each. There's clearly a difference in the mean values, and the scores go up. If I set this up as a paired, two-sided hypothesis, I'm now changing from assuming that grades could only go up in this intervention. Now I'm allowing that grades may also go down. But you see what happens, even though the data are exactly the same, the p-value is twice the size when I run with a two-sided expectation. So if you leave out this alternative equals less business, suddenly the p-value that comes back is different. The reason here is that if you are able to disprove the null hypothesis in only one direction, the p-values that you get back will be half the size for a given set of values. If you specify that a two-sided outcome is possible, that maybe grades went up because of the biostatistics module, or maybe grades went down because of the biostatistics module, you're no longer able to discern an effect. So there's this twofold improvement in your ability to get a significant p-value for a given data set if you're able to discount one of the two possibilities. To say we only care about values that are rising. We don't care about values that are also falling. Now, what happens if I do an unpaired one-sided test? Does that cause my p-values to become essentially useless? If I lose sight of the fact that this particular value in A should only be compared to this particular value in B, my p-values aren't significant at all. So how you structure your t-test, what parameterization you use with it, is going to have a large impact on the magnitude of p-values that come out. Anytime you have paired data, you must tell t-test or u-test that that is the case. All right. So difference testing is absolutely essential in biomedical research. It can certainly be misused. We've looked at some examples where if you misparameterize the t-test, you end up getting a t-statistic and you end up getting a p-value that's not significant even when there's obviously a relationship between the numbers. So always you should make effort to see that if you're using Welch correction, you know why, that you have a difference in variance. If you're using a one-sided versus two-sided test, you should understand why. If you're using a paired test, you should know why. So I don't know about you, but I allowed the year 2008 to go by without celebrating this remarkable paper. A beer manufacturer's employee published a difference test that in a lot of people's minds equals biostatistics, and 2008 slipped by without a centenary celebration. I think this is kind of sad. Maybe we should all drink a Guinness to celebrate at some point. Finally, next, be sure you know whether or not your data are paired. Leaving out the paired parameter when you run a t-test, if you should have used it, is going to be highly detrimental to your finding differences. When your data are irregularly distributed, opt for a non-parametric test instead. I think just a few slides ago we were looking at the case when I had a ringer in my A set. I had one experiment that was a significant outlier to negative values. If I were to assume that t-test will just take care of it for me, I would be very, very wrong. Now, that said, if you're going to compute a u-test instead, you'd really better have more than a 3-on-3 comparison. One of your assignments is going to be evaluate the effectiveness of u-test in the context of a 3-on-3 comparison, a 4-on-4 comparison, and a 5-on-5 comparison. So we're going to find out just how, what score we get, what p-value we get for perfect separations in each of those cases. I think you'll be surprised to see how big an impact you get from having 5 replicates rather than 3. Okay, with that said, Guillen has you this afternoon. I will see you again on Thursday at 9:30 in this room again, I think, where we will be talking about one-way ANOVA, which could be terrifying, but I want to tell you, one-way ANOVA is just like t-test with more than 2 cohorts. So it's actually going to be kind of fun. I'm looking forward to that. In the meanwhile, please do take a look at the assignment. I tried to keep it very in focus for the kinds of things you must know to be ready for your own research projects. So I look forward to seeing your results. Thanks, everyone.